Okay.
So welcome everybody. It is a pleasure to have with us today Tassos Bountis. Looking at the audience, I'm sure that everybody knows him. So I will skip further introduction. Tassos gives from time to time talks, seminars in our series. So we are glad to have him with us today. You see the title, damping effect of Caputo fractional time derivatives nonlinear wave equations. So at least for me, it's not clear what is the topic about, but right now Tassos will tell us. So Tassos, please go ahead.
I hope you will find out soon.
Yeah, exactly.
Yes. Well, σας χαιρετώ όλους, παιδιά, και I greet everybody. Again, unfortunately, I'm in Patras. It's not easy for me to come to Athens all the time, but I will speak in English. I hope we will have some audience from foreign countries to follow. And I want to start with an apology because I should have changed. This is a title of a paper you sent or something to the journals. But if you want to attract an audience, you must make the title a little lighter. So you will soon find out that, in fact, what I will tell you about is a very surprising phenomenon that happens in the systems you like so much. Everybody at the Institute, you like very much conservative systems that conserve a certain quantity. We usually call it the energy or phase space volume, but nevertheless, there is a conserved quantity. And you expect that in a conservative system, there will be periodic solutions, there will be quasi-periodic, there will be all of the things we know, but the difference is that all of the things we know refer to derivatives with integer order. And the time derivative is of second order, Newton's acceleration, and the space derivative also used in Laplace's equation or so many other ways, always of a second order. So what happens for nonlinear waves, for example, when you have both of these terms in a partial differential equation? That's attracted the attention of my colleagues and my co-authors, as you will see below. But the first surprise came to us, to myself and to my co-author, after we had published the paper. So this is the idea. This is a surprise talk about the system. And in fact, the one who introduced me is Jorge Eduardo Macias Diaz. He's an author, co-author of mine for many years. And we worked on many times on integer derivatives, but he knows a lot about fractional derivatives. And he told me we should work on this together, Tassos. Okay, so we did. But the others got into Panos Keverkidis, very well known in nonlinear wave equations with books and papers and so on in Massachusetts, and his two collaborators were very surprised when they saw what we had to tell them. And the realization, the wake-up call, came with the first paper that you see here, Dissipation Preserving Scheme for a Caputo Fractional nonlinear equation. Here, my friend Jorge Macias Diaz had done most of the mathematical work to prove that the system is conservative and that the numerical analysis he uses very much is conservative. So I worked with him on the theory and the equations and so on. We did the calculations, we published the paper, and then we saw that the title should be a dissipation non-preserving scheme. There was, we thought that it would be conservative, but then the pictures came out, and even the referees did not notice. It was so nice, but they didn't see something that a physicist will recognize immediately. And my friend Jorge Macias Diaz is more of a mathematician. So then other applied mathematicians came into the story, and I will tell you how it all developed with three, and we have a fourth paper coming up also. So how does the whole thing start? Well, suppose we choose, so I have some questions for you for the beginning, make it more friendly. So, but we will discuss this in the end. Just keep them in your mind as we go along. Suppose we choose a differential equation to describe a physical phenomenon. We do that all the time. What do we do? First, we have to worry about the terms for the potential, where these equations comes from, chemistry, biology, should it be dissipative, should it be conservative, the planetary dynamics and gravitation, all of these things are fine. And then we begin to solve it. Now, one might ask us the question, what happens if, as you know, all derivatives, uh, whether it's with respect to time or with respect to space, are very local quantities. They describe a slope of a plane or a tangent or a change in the time, a change in the time at a very, very specific point. Now, many people speak about non-locality and they introduce a kind of delay equations, things like that. But also, non-locality means if we change the order of the derivative, and instead of your favorite alpha equal beta equal to 2, as we put in space and time, alpha and beta equal to 2, and we do all our work so far, let us change it to 2, to less than 2, to greater than 2, positive always. And so, why do it? It's not a game. It's a story that began tens of years ago. It started actually centuries ago when first mathematicians, famous mathematicians, thought about it. Even who was it? Very important people worried about changing the power of the derivative. But here we have now fractional dynamics, fractional mechanics as a new field. And fractional equations, differential equations, come into biology now, into economics, into models about COVID virus progress, you name it. And they all find dissipative results because they're interested in chemical, biological models. And they have limit cycles, they have fixed points, they have all of this. So we thought that in a conservative system would be interesting to study them. And what should we do? Shouldn't we include them to understand a little bit non-local? Will this improve the accuracy of our description? We will find out that it leads to the wrong results in the case of conservative systems. This is the surprise. Now, wrong results should be quote unquote. What do you mean wrong results? Maybe they are correct results, but in another framework. So let's see first what happened in the story, taking things from the beginning. Now, we will study here partial differential equations, but I will mention ordinary differential equations also. So we will try to use this power of fractional calculus to understand how we have a time derivative called beta, and that should be 2 in classical analysis. And we have a spatial derivative, alpha, and that should be 2 in classical analysis. The same thing holds true, of course, when you deal with wave equations, like the Klein Gordon equation. Very, very famous and well-studied equation. Integrable if alpha equal 2. So what happens if beta is different than 2? Then you see dissipative behavior. As soon as beta becomes 1.9999, dissipation begins to set in. We will not consider very much beta greater than 2 because that leads to divergence. It's the opposite. And you will see that phenomena like saddle point phenomena will occur in the development of this theory, of this approach, whereby you will see solutions going to infinity or solutions going to a fixed point, oscillations, and so on. So interesting phenomena will occur. For example, for alpha less than 2 in space, we will find that kinks can be attracting. And kinks, you know what it is, right? This Riesz function that, like a wave that goes to the right or the left. And if it goes to the left, I think we call it kink. To the right, we call it anti-kink, etc. So one wave going to, and they usually come also together as a binary solution with kink and anti-kink behavior. Now, so what are the new animals we are going to discover in this voyage? Let us begin by setting up the problem. The problem is that we have a second-order differential equation, just like all applied mathematicians studied, Beta should be 2 in the ordinary derivative time. Alpha should be 2. This is the spatial ddx square. This is del x square, second derivative partial with respect to x. There is a potential. Now, for the potential, we will always choose f of phi is 1 minus cosine u. That leads us in the derivative, it is the sine Gordon equation. And we will start to play with various values of alpha and beta. So let's prepare to play a game and see what we discover. Now, we will even make it easier. We will begin with a known exact solution of the problem. And this is the very well-known breather, whereby you have a mountain, a little mountain, that goes up and down in time, like like a wave. But a wave with a circular kind of form, as you will see now, going on forever. Okay, well, that's exactly what happens when alpha is equal to beta equal to 2. So when we applied our approach with Macias-Diaz numerically and set up all of the second derivatives in all the generality as numerical partial differential equations, we set alpha equals beta to 2, and we got what everybody expected, the numerical solution of our publication on the left and the exact solution on the right. This is what you expect from a nonlinear wave equation. But then we said, let's now try to, here we were scared. I mean, alpha is less than 2, beta is less than 2, and strange things happened. So for different values, beta equal 1.6 is on the center, beta equals 1.2. This weird solution on the left that didn't show any oscillations, but showed something like an approach to a saddle point, a fixed point solution, some kind of a localized wave solution. And the others, when beta was greater, 1.6 and 1.8, were clearly dissipative. That was the first thing that, as I said, we started to see this after the paper. And now let's make alpha greater. And again, you will see this appearance of these solutions, which we did not follow long in time. This was something we didn't do at the first paper because we're not interested in that. We just left it and said, this must be something we should return back in the future. So what happens in time? These are very short time integrations, and we'd like to look at this phenomenon in greater detail. So what is going on here? Well, let's start with a detailed study for alpha equal to 2. We let the space derivative be 2, and let's not touch that. And let's suppose we have non-locality in time. So we have beta, and beta greater than 2 led us to escape to infinity. And if that's what happened always, of course, we would throw the whole thing in the wastebasket. But we understand that for beta, we have divergence. But for beta less than 2, we have to we calculate a Caputo time derivatives. Now, these can be found also in the papers. They are really strange expressions, and if you haven't seen them before, you have to really look at the literature. But this is the way people define the spatial fractional derivative. That is a Riesz type, and that is okay. In fact, I have seen papers on solitons where the Riesz total derivative is fractional, but the time derivative is Caputo. And they found solitons, integrable behavior, conservative behavior, no problem. The real, not, I don't want to call it a problem. The new direction of research here is actually to change the Caputo time derivative. And there are other fractional derivatives also. If you have seen anything in the literature, there are different time derivatives, not only Caputo and Riesz and so on. But the Caputo derivative has some very, very nice behavior. At 0, you can define your initial conditions much better. The derivative of constant is 0. You know, this doesn't happen with all fractional derivatives. To take the derivative of constant and find it's not 0. But with Caputo, you find all that. So we are doing something that many thousands of other people are doing in this system. We're proceeding in this direction. And what happens now with my new colleagues, Panos Kevrekidis and his group, we repeated the calculations we did with Jorge Macias Diaz. And indeed, we saw that we have, for long times, we have the kink behavior, the breather behavior. So we have a breather now on the left. And that's what it was also for beta equal to 2. You saw these two mountains going on. It's a breather that's going up and down in space and time. And now you see that as soon as beta is less than 2, 1.9, 1.199 here, 1.9 here, and 1.5, the whole thing disappears. So here is the problem. What do we do with this system? Then I asked myself, when I thought about that, I said, let's go to the books. You'll find wonderful books on fractional calculus. Let's go to the harmonic oscillator. What do these guys do? I go to the harmonic oscillator that you see before you, and there's a scaling for omega to put it in beta. So beta equal to 2 is the well-known harmonic oscillator. So to make the formulas below more simple, we took this oscillator, and we know from the books that the solution is a so-called, very famous for the mathematicians, Mittag-Leffler function that you see in number 9. Well, let's look at this Mittag-Leffler function. And to your surprise, you see that if the Caputo index beta above, forget it, total dissipation, beta is equal to 0.25, 0.5, 0.75, 1, there is monotonous dissipation. As beta starts to wake up and move towards 2 and becomes 5 over 4, 3 over 2, then you see the oscillations becoming bigger and bigger. And we return for beta equal to 2, the last value, we return to the dash dot final oscillation, which is perfectly periodic. No problem. Anything below 2 will lead us to this phenomenon. No, but we're not talking about oscillators now, harmonic oscillator and all that. And nobody stresses that also in the literature. This seems to be fine. If you introduce non-locality, you find dissipation. So what? Yeah, but we cannot do that. We have to understand it. So then we said, well, let's see now. What if this damping is linear? As we usually do put some linear damping in our equations, right? And if we discuss even phenomena in celestial mechanics, we might allow some damping to be present in the atmosphere or somewhere. So we can add, usually, what do we do? A linear term in time, right? Which is positive. Okay. If our damping now that we discovered is of this type, we should be able to eliminate it by adding a term that you see here, gamma dphi dt, where gamma is negative. Okay? Gamma positive would be dissipation. So gamma negative is anti-dissipation. So if what happened is of this form, this term here will, for the right choice of gamma, should eliminate the problem. Tough luck. Unfortunately, this led us to a saddle point. We were able, in other words, to choose a gamma. You see here we have a critical gamma C. To choose a gamma so that we were tracking the solution and eliminating the dissipation for some time. But always, for any gamma we tried, even the gamma C was the best results we had, we are able to follow the oscillations, reproduce the frequency for a long time. The amplitude, you see. So the red and the blue, we were able to match it and try to want to eliminate the other. But it's not the same phenomenon. You see, the red one is now growing. You can match the amplitude, but you cannot match the frequency. So it's not this type of anti-damping. It's not so simple. In fact, you find that there is a kind of new behavior even for that equation I showed you before. You get what is called kink anti-kink formation. The frequency is fine. Here you see frequency is 0.8 or something. Yeah. So we are chasing a periodic solution. We are chasing it, chasing it, chasing it, reproducing it for a long time, but then it escapes us. And what we find is opposite moving kinks. So now there is new physics here in this case. The solutions are not trivial, and even this term we added is artificial, damping. We might as well remove it and sit down to study the phenomenon a little more seriously, because new physics is going to be discovered that way. If the now you see the mathematics is leading us to a new solutions which we will like very much to see in nature. Now, okay. So now let us take things more seriously and say, suppose we have a beta equal to 2. Can we find double kinks? Alpha will be greater than 2. So now, as you see here, we find a solution for that case, beta equal to alpha equal to 2.5, typical for this. And as soon as we change, and then we take the proper initial condition that we choose. What does it look like? Looks like a Sess function, right? Look here down. What do we start with in this physical problem? Well, let's start with an initial Sess function, like a blue function. Or let's start with, now what will be the amplitude of this mountain solution? Well, if the width is bigger, then you choose your initial condition accordingly. You want to follow the red one or the one inside the solution that we found to be like a steady state. Go inside, choose a sharper Sess function, like a black one, and you will see it go to 0, disappear. Go outside this bell-shaped curve, choose a red one, which is the Sess 0.4 solution, and you will see your solution going away and forming two kinks. So those two kinks are here to stay. Let's look at it a little more now for alpha greater than 2. Again, you see that we have a kink-anti-kink pair which attract each other now, and they form a single solution, and that's for alpha equal to 2. But in the bottom figure, we also see we have this equilibrium configuration, but when we change alpha a little bit, I don't see now, I must have written it. We change the alpha, then this solution that we saw here can go into a different type of wave, which is the kink-anti-kink wave. So we begin to see unstable points in phase space, which can last for a very long time, but then a small deviation of the solution will lead you to a kink-anti-kink solution which travels in phase space. So we can put boundary conditions, periodic boundary conditions to trap it, to keep it a little bit, but it's a very, very well-known phenomenon in wave dynamics. Well, and now comes the question, what about if we put fractionality both time and space? So far we had looked at them separately. So now what we're going to do is, what kind of new animals are we going to discover? Well, we can have a Caputo derivative of order beta different than 2 and keep alpha equal to 2, or Riesz derivative alpha equal to 2, and then vary them both, etc., and see what happens. And now you will say, again, what do you start with? Well, again, a good idea is to start with a single kink solution that has a typical waveform in these models is the single kink. Consider our Riesz derivative alpha equal to 2 and values of the Caputo. So we have an initial condition. We have an initial condition also with a Lorentz contraction factor also, which we know to be exact in the classical case of the wave equation. So now we can change the V0, the speed of the wave, try to see what will happen to this initial condition. How will it evolve? In the classical case, we know it's going to be a kink, it's going to be a traveling soliton. We know what we expect to see. But what are we going to find out now? And the surprise comes when we vary alpha, but keep beta equal to 2. Then it is possible for alpha greater than 2, you see alpha 0.25, 2, and alpha equals to 1.5, we get a single kink. Wow, that is possible. Not only fancy results of kink anti-kink for pairs and all that, even a single pair can come out. And now, because we know how to analyze the stability, it's a simple nonlinear wave equation, and we see that all the eigenvalues, as you see, even the larger one, the red one, are less than 1. Imaginary. It's imaginary. So lambda squared is negative, so lambda is imaginary. So we have stability. So the kink has some little deformations on the top and the bottom, but it exists. So it seems that this case is good for physics, classical physics as we know it. However, there are the double kinks again. Now I'm going to take alpha equal to 2 and reduce beta. And you see, for beta equals 1.95, a little less than 2, the double kink, the kink-anti-kink pair with which we started before, the analytical solution, we had it, and we started with a kink-anti-kink pair, initially separated by this distance, is now coalescing into a traveling soliton wave here. On the left panel is the breather is vanishing. I'm sorry. This was not a breather. This was not the two double kinks. Anyway, it's like a breather. The breather is vanishing, and the two breathers collide, and they give us one single breather. Where the right panel, we get a quasi-elastic. Now, if we vary the V0, V0 is the solution, and I think this should be here 5.6. I shall cover because 5.9 is yeah, the quasi-elastic collision is 5.9. Anyway, this is a detail. The point is that when V0 changes, the new animal we obtain is not an oscillating breather type solution, but it is again a double kink. That is unstable now, and the kinks separate each other and go away. And again, we focused on this phenomenon that I told you, and it's possible to see that for beta, we keep beta equal to 2, always. The time derivative is, but space is non-local now. Alpha is greater than 2, and what do we find? We find again, in some cases, choosing our SES profile, as you say, you have to start with the initial condition, and the initial condition here is a nonlinear wave. So you begin with a very well-known nonlinear wave, like a soliton, and you see what happens to it. And sometimes you can see it oscillate beautifully as a breather for a long time. But if you change the initial condition, it's not an integrable system. It's not going to be a soliton anymore. It's going to be a separation of two kinks, double kink solutions, steadily separating away from each other. So we are beginning now to form the zoo of kind of solutions we expect in this problem. And indeed, if now both alpha and beta change, we can see that yes, with beta less than 2, we get dissipation always. You can't avoid that when beta is less than 2. Before you saw beta equal to 2, kept the wave for a long time. As soon as beta equal to 2, here is again what we saw before. We can lose it. We can lose it. But depending on the initial conditions, and that's the beauty of the wave equations, you can either lose it. Excuse me. Κυριάκο μου, δίνω μια ομιλία στο κέντρο της Ακαδημίας. Θα τα πούμε αργότερα. Ναι, με συγχωρείτε. So, as I said, before, we do get the dissipation, but it depends on how you start now. As you saw before, if you start with a small wave, you will lose it dissipatively. If you begin with a bigger mountain from the beginning, it will open up into two kink anti-kink waves going away from each other. And you will see that again we have kind of saddle points in phase space where we can witness a rich, I would say, family of solutions of the type of kink type. And so you see, uh, I didn't want to tell you more details about what we found and how we have studied it further in our recent paper now, but we must live with the reality that PDEs or waves, nonlinear waves, are not conservative if alpha and beta are not equal to 2. And uh, any kind. Now, an idea comes to my mind. We didn't study the linear case. Alpha equal beta equal to 2 is even the linear waves, but I am sure what will happen. Even if if we study the linear wave, we see it dissipate just like the harmonic oscillator. Because the harmonic oscillator is linear, and as soon as you change beta from 2, you get dissipation. So the same thing will happen to a linear wave, I'm pretty sure. Now, in nonlinear waves, we have a rich phenomenon, new possibilities of results of waves that you never see, of course, in linear wave equations. And so we discovered that. Just a quick summary, we saw that it wasn't just a simple dissipation, linear type that we have known for a long time to exist. This is a different kind of dissipation that it is built into the partial, fractional derivatives, and we have to live with it. If we want non-locality, we must live with dissipation. This is what is the conclusion in my mind. If you want to introduce non-locality, you must necessarily live with dissipative behavior. So we observed single kink dynamic, kink. These were the actors in this play. We played with single kinks, and the kinks became kink and anti-kink pairs, which either moved away from each other, as you saw, or they re-emerge, forming some kind of soliton behavior. And the kink anti-kink solution is unstable. And so, as you see, these new wave phenomena are now ready to, they are published. Yeah, it will appear in the Journal of Mathematics in a few days. So, important question for all of us. Do fractional derivatives introduce artificial dissipative effects? I think I have convinced you the answer is yes, they do. And even if you, at least when you vary the time, you see, because if the time is integer, then time is local, then the spatial derivatives will not be so surprising if we make them fractional. So fractionality in time is the major. And that's what I mean here. What does this imply for non-conservative dynamics? What should we do? So I end by telling you that, yeah, we are preparing to edit a volume of the journal, Fractal Fractional. It's an MDPI journal. We have some possibility for allowing authors to not to pay, give some for free, as long as the paper passes by referees and it's a good paper and so on. So I do have the possibility to invite people to write a paper and reduce the amount they pay because I know how expensive these journals are. So we hope that we will have some good response from authors and that my colleague Macias Diaz and myself will have a good volume to contribute and certainly try to answer the behavior of dissipative effects. Okay, I will now, shall I turn it off? No. Okay, I'll keep it down.
First of all, thank you very much.
I'll keep it down. Okay.
So, thank you very much. That's all.
I hope it is entertaining. How long did I take? Not long, huh?
Not much, so there is time. But thank you very much. It was a little bit surprise also for me. It's for me this fractional derivatives sound a little bit exotic. Uh,
Yeah.
it is really very surprising how by changing this, let's say, beta index, then you pass from dissipations to conservative system, etc. Do you have in mind any kind of physical system that this variation would show us a different kind of behavior? And does it have a physical meaning or system that we want to see the
Well, as I said, the main idea was non-locality.
yeah,
That is, that's what made everybody write books and hundreds and I mean, not to say thousands of papers, which are in the literature. And in the beginning, I had the same reaction. Well, they found a new game. So, mathematicians play with a new game, and they all jumped on it because they could apply fixed point theorems, uniqueness of solutions, hundreds of papers that prove there are fixed points and there is stability and uniqueness. So what? But then with this permission of non-locality, say we have non-locality, they went into sciences like biology, economics, engineering, you name it, and everything was fractional. So for a long time, I did not worry about it very much. I said, well, it's a new game, so they're playing the game. But when I did it, and I found in a conservative system dissipative solutions,
that's
I
it.
started to, yeah, you see what I mean. So I do believe that some kind of non-locality, yes, in space, perhaps will be allowed, and we can have that new solutions, new phenomena. But non-locality in time seems to lead to dissipative behavior. And if you like to study dissipative behavior, Panos, you see, if you like it, then it's not only done by this artificial plus gamma dx dt we put in, right? That's what we do. And physicists do that all the time. But who told you the damping? In fact, there are different kinds of damping, and there are many engineers who are very much against this gamma dx dt, linear derivative. Ah, με συγχωρείτε ρε παιδιά. Κυριάκο, θα σε πάρω εγώ, είμαι σε μια συνεδρίαση. Εντάξει. Ναι, ναι, θα τα πούμε. You see, so instead of adding a damping term of your own choosing, even if you're an engineer, they have different kinds of damping. Why do it this way? Why not do it by allowing things not to be local? That sounds like a good place to start. So the thing is open. These questions are open. I mean, in a conservative system, for example, yeah, don't change the time. Let the second derivatives, the Newton equation, all of that hold. But if you have a partial derivative with respect to x, then you have, yeah, so it's nonlinear waves in celestial mechanics. You must have PDEs of that kind, right? Also, celestial mechanics is not only ordinary differential equations. So if you have a wave equation in celestial mechanics, it would be interesting to look at it that way.
Very, very interesting. Very interesting. We do have waves, but we didn't think
You
of
have, yeah, waves. Yes,
wave
you have waves, but
dynamics.
gravitational waves. You have gravitational waves, right?
Well, the
Okay.
for of us that it comes in mind, I'm sure, are density waves. Let's say density waves as the bar and spiral perturbations propagate on disk of galaxies.
Okay. If you have density waves, you have partial derivatives with respect to time also and space. And space?
Yeah, both. Yeah, okay.
Yeah. Okay. So you don't touch the time, but you can change the space derivative. And, you know, uh,
I'm wondering if it has a physical meaning. I'm a little bit confused, to tell you the truth, but okay. Well, let's see if other people have questions here.
Carvalho, Rotulas.
Ask one question.
Can,
Have you ever seen the reverse effect, the other effect? So when you change the rank of the derivative, you find dissipative behavior in a well-known conservative system.
Right.
Okay, if I'm right, maybe the question is wrong. So can you see the inverse phenomenon? If you start with an open system, okay, that you know from that it is really dissipative, are there any coherent solutions when the time derivative changes, or when the rank changes? So if you find, if you see that there are the
Yeah, you see,
point.
yes, Thanasi, you're right, I understand. But you see, yes, it's a good idea if you have a knowledge of what the dissipative terms are like. And because they're usually artificial, this is the point. That's why we also took the linear term. To study linear derivative is usually artificial way to introduce dissipation. If you're sure your dissipation is physically explained, right, and supported by yes, then it does make sense to change it, right? Because it's not going to be just what we tried, just a linear term in the first derivative.
Find
Yeah,
forms or quantities that are like coherent states. I don't know. I know
yeah,
states from light.
right.
Light, which
Yes, coherent states could be like traveling waves, like
yes.
yeah, like
Okay.
a traveling. That's what I showed. There are coherent states here, and some that are no diverging waves going to infinity. But then if you have a closed phase space, then this wave will periodically travel around. But it's a good question that if you have some form of dissipation inherent in your problem that you are sure is the valid one, then it's a good idea to play with the time derivative.
Okay. Thank you.
Let's see what will happen.
So,
So, you see, Panos, that's the idea that
yeah,
mathematicians can go on their own road, discovering new phenomena, but usually, usually that's the start of a new discovery, right?
and
It has happened. So don't say no to it. It's
no,
an interesting field.
the challenge to understand it, of course, and try to apply.
Right. But we do tend to shy away from it and say that, oh, this is not something I understand. I never dealt with it. It's a curiosity phenomenon for mathematicians. But when the years go by, you discover many applied scientists are using it. Then you wonder what is really going on. So, anyway, I hope I surprised you a little
Yeah, sure, you did. But
with
are other questions from the audience here or online if one wants to have a question?
new phenomena.
Oh, okay, then thank you again.
Good. Okay, thank you.
And I remind everybody that there is your talk on Thursday, right, at COSA?
At Cosa, yes, I will go and speak to them also. And I'm sorry I couldn't be there today,
We can follow it.
but yes, it'll be good to see it second time.
Okay, okay. Also in person, people can.
You will be.
Yes, I will be there and we can discuss.
There.
Good. Well, thank you very much for the invitation.
Thank you very much, Tassos, and I hope we have the opportunity soon to have another talk also.
Yeah. Αυτό είναι, this is what we call in Greek, κενά δαιμόνια.
Δαιμόνια.
Αυτό που λέμε κενά δαιμόνια. It's new demons coming into our life from mathematics. Good. Okay.
Great.
I'll see you later. Bye bye, guys. Thank you.
And with you. And with you.